Good morning. Today I am going to deal with the relationships between the equilibrium constants. In the previous video lecture, we studied about various equilibrium constants like Kp, Kc and Kx. Today I am going to discuss about the relation between Kp and Kc and Kc and Kx, etc. We know that PV equal to nRT, that is our ideal gas equation, where R is the universal gas constant. Or we can write P is equal to N by V into RT, which is equal to C into RT. Here C is the molar concentration of the gas. C is equal to number of moles of the gas per unit volume. Consider the general reversible gaseous equation reaction, that is A plus BB plus etc. gives LL plus MM plus etc. What is the expression for Kp? Kp is equal to P L to the power L into Pm to the power M into etc. all divided by Pa to the power A into Pb to the power B into etc. where P is the partial pressure and we know that P is equal to CRT. So substitute this equation in this equation. We can write Kp is equal to CLRT all to the power L into CMRT all to the power M into etc. divided by CART all to the power A into CBRT all to the power B into etc. which is also equal to CL to the power L into Cm to the power M into etc. RT whole raised to L plus M plus etc. whole divided by Ca to the power A into Cb to the power B into etc. into RT all raised to A plus B plus etc. Here we can say that Cl to the power L into Cm to the power M divided by Ca to the power A into Cb to the power B equal to Kc. So we can write Kp equal to Kc into RT raised to L plus M plus etc. minus A plus B plus etc. Or we can write it more simply as Kp is equal to Kc into RT raised to delta N, where delta N is the change in number of moles in the reaction. That is delta N equal to number of product molecules minus number of reactant molecules in the chemical equation. So the relationship between Kp and Kc is Kp is equal to Kc into RT raised to delta N. Then another important thing is for a gaseous reaction, delta N will be equal to 0. Then the value of Kp will be equal to that of Kc. Next is relation between Kp and Kx. We know that P is equal to X into P. Here P is the partial pressure of any gas in a mixture of ideal gases, which is related to the total pressure P, as P is equal to X into P, where X is the mole fraction in the mixture. So substitute the value of P, that is our partial pressure, by this equation. We can write Kp is equal to XL into P all to the power L into XMP to the power M into etc. divided by XAP all to the power A into XB P all to the power B into etc. or which is equal to XL to the power L, which is equal to XL to the power L into XM to the power M into etc. whole divided by XA in to the power A into XB to the power B into etc. into P raised to L plus M plus etc. minus A plus B plus etc. or which can be simply written as Kp is equal to Kx into P into P raised to delta N, where delta N represents the change in the number of molecules in the reaction. That is, delta N is equal to number of product molecules minus number of reactant molecules. Then what is the relation between Kc and Kx? The first equation is Kp is equal to Kc into RT raised to delta N, and another equation relating Kp and Kx equal to is Kp equal to Kx into P raised to delta N. In both these equations, LHS are same. So we can equate these two equations like Kc into RT raised to delta N equal to Kx into P raised to delta N. Or we can write Kx equal to Kc into RT divided by P all raised to delta N. We know that RT by P is equal to volume V. So we can write Kx is equal to Kc into V raised to delta N. That is the relationship between Kc and Kx. From all these expressions, we can see that if delta N equal to 0, then all the equilibrium constants will be equal. Next, we have to discuss about the significance of reaction quotient Q. We know that the Van Hoff reaction isotherm, that is delta G is equal to delta G0 plus RT ln Q, where Q is the reaction quotient or activity quotient, and which can be expressed as A L to the power L into AM to the power M into etc. divided by A to the power A into AB to the power B into etc. For a general reaction, AA plus BB plus etc. gives LL plus MM plus etc. That is our normal general equation, and here Q is the reaction quotient or activity quotient. And this reaction quotient may be expressed as QP and QC. Then what is QP? QP, here the activities of the constituents are replaced by their partial pressures for a gaseous reaction. And what is QC? That is, here the activities of the constituents are replaced by their molar concentrations. Then what will be the equation for QP and QC? Qp is equal to PL to the power L into PM to the power M into etc. whole divided by PA to the power A into PB to the power B into etc. Where time will be a specific time, that is time equal to T. Then what will be the expression for QC? QC is equal to CL. Here C represents concentration into Cm to the power M into etc. whole divided by CAA into CBB into etc. Here also these are not necessarily equilibrium values. All these reaction quotients are at a specific time T. Then the determination of the reaction quotient, that is our QP or QC at a particular time T, and its comparison with the equilibrium constants. These are equilibrium constants. Kp, Kc, Kx are equilibrium constants, whereas Qp, Qc are not necessarily the equilibrium constants. That is a constant for a specific time T. Then when we compare with QP and KP or QC and KC, that study will help to predict the direction of a reaction. That is, if Kp less than, if Qp less than Kp or Qc less than Kc, the net reaction will proceed from left to right in the direction of the products to attain equilibrium. That is, the reaction will be forward reaction. If Qp is greater than Kp or Qc is greater than Kc, the reaction will be reverse to attain equilibrium. Then if Qp equal to Kp or Qc equal to Kc, the reaction mixture is already at equilibrium and there is no net reaction. So the determination of Qp and Qc will help to predict the path of a reaction. Next is a very important derivation, that is temperature dependence of equilibrium constant, or it can be called Van Hoff equation. We know that delta G0 is equal to minus RT ln Kp. That is already we derived the relationship between the equilibrium constant Kp and Gibbs energy change, standard Gibbs energy change, delta G0. On differentiating this equation with respect to temperature at constant pressure, what will be the equation? Dou by dou T of delta G0 at constant pressure equal to minus R into ln Kp minus RT into d by dt of ln Kp. Here T into ln Kp. Here R is constant, and on differentiating T into ln Kp, first we differentiate by taking T as a constant, then differentiating Kp as a constant. So we can write minus R into ln Kp minus, here ln Kp is a constant. So on differentiating t with respect to t, we get 1. So the first term is R ln Kp. The second term, here t is a constant and we differentiating ln Kp, that is d by dt of ln Kp. Then on multiplying throughout by t, we get t into dou by dou t of delta G0 at constant pressure is equal to minus RT ln Kp minus RT square into d by dt of ln Kp. That is minus RT ln Kp equal to our delta G0. So we can write T into dou by dou T of delta G0 at constant pressure is equal to delta G0 minus RT square into d by dt of ln Kp. And we know Gibbs-Helmholtz equation, that is delta G is equal to delta H plus T into dou by dou T of delta G at constant pressure. Or under standard condition, we can write delta G0 is equal to delta H0 plus T into dou by dou T of delta G0 at constant pressure, where delta H0 is the standard enthalpy of reaction. So T into dou by dou T of delta G0 at constant pressure is equal to delta G0 minus delta H0. In these two equations, LHS are same. So we can equate both these two equations and we can find that delta H0 is equal to RT square into d by dt of ln Kp, or we can write d by dt of ln Kp is equal to delta H0 divided by RT square. This is our important Van Hoff equation. Next is integrated form of Van Hoff equation, that is d ln Kp is equal to delta H0 divided by RT square into dt, that is our Van Hoff equation. On integrating this equation, and let Kp1 and Kp2 represent the value of equilibrium constants at two temperature T1 and T2. So on integrating this equation, we can write integral Kp1 to Kp2 d ln Kp is equal to integral T1 to T2 delta H0 divided by RT square into dt. Or we can write delta H0 divided by R. This term is a constant, so can be taken outside. Then integrate T1 to T2 1 by T square into dt. Or we can write, which is equal to d integral d. Both are cancelled and we can write ln Kp2 divided by Kp1. By applying upper limit minus lower limit, we can write ln Kp2 divided by Kp1, which is equal to delta H0 divided by R into minus 1 by T2 minus 1 by T1, or we can write delta H0 divided by R into 1 by T1 minus 1 by T2. That is ln Kp2 divided by Kp1 is equal to delta H0 divided by R into T2 minus T1 divided by T1 T2. Converting into logarithm, we can write log Kp2 divided by Kp1 is equal to delta H0 divided by 2.303 R into T2 minus T1 divided by T1 T2. This equation are known as integrated Van Hoff equation. And this equation is very useful to calculate the equilibrium constant at one temperature if another value for another temperature is known. So, lot of problems are based on this integrated equation. Hope it is clear. Thank you.